Hello, my name is Boyan Wang. I graduated from Fudan University in China in 2018. I am currently a third-year PhD student in CPAS, Virginia Tech. My advisor is Dr. Yuhao Zhang. My research interests are ultra-wide bandgap semiconductor power devices simulation and fabrication. My presentation topic today is high surge current capability in ultra-wide bandgap gallium oxide power rectifiers through device package co-optimization. We studied the surge current capability of gallium oxide power rectifiers, and we found that the double-side cooled gallium oxide Schottky barrier diodes with a 3 x 3 mm square Schottky contact area can sustain a peak surge current over 60 amp, with a ratio between the peak surge current and the rated current superior to that of similarly rated commercial silicon carbide Schottky barrier diodes.
First, let's talk about the advantages of gallium oxide. Gallium oxide is a semiconductor material with ultra-wide bandgap, and therefore it has higher power device figure of merit compared to silicon carbide and gallium nitride, which means that, potentially speaking, it can have lower on resistance at the same breakdown voltage level. Although the commercial gallium oxide wafer is expensive for now, but in the future, in large-scale industry manufacturing, they can be much cheaper than gallium nitride and silicon carbide substrate because of the melt-based crystal growth process. Now let's talk about the promise of gallium oxide for high-temperature applications. As we all know, as the operating temperature for power systems goes higher and higher, there will be many problems. Silicon power devices are limited to a junction temperature of 150 degrees C because of the high intrinsic carrier concentration in silicon. Carbide MOSFETs are limited to a junction temperature of 250 degrees C because of the inherent instability in oxide interface and contact. However, gallium oxide, it has an ultra-high melting point, and it has much lower intrinsic carrier concentration because of the wide bandgap, which means that controllable doping at higher temperature can be achieved. And thirdly, thermally stable Schottky contact has already been developed. But gallium oxide, it has a very low thermal conductivity, which is only about 5% of silicon carbide. So therefore, we want to ask the question, are the electrothermal ruggedness performance of gallium oxide power devices? Now let's talk about the surge current test. Surge current ruggedness is essential for many power applications where the device needs to temporarily sustain a current much higher than the rated one. And here's our test board schematic. Surge current in GVAC standard means a 50 Hz half sine wave is applied on the device under test during the test period. And here's a photo of our test board. This is a test demo, and there are 3 steps. In step 1, the capacitor is being charged. In step 2, the energy stored in the capacitor, the LC resonance will create a half sine current wave on the device under test here. And that's the test period. Now let's talk about a double-side cooling package design, which allows the heat dissipation by the gallium oxide chip and from the Schottky junction simultaneously. In a 10 millisecond surge test, all the heat generated will be dissipated inside these 2 silver plates. From PCAD simulation, at the peak temperature moment, which is around 6 milliseconds, high temperature appears inside the gallium oxide diode. But at the boundary of the 2 silver plates, it is very close to room temperature. At the end of this 10 millisecond surge test, part of the heat is transferred to the anode silver plate, but the temperature of the anode silver plate is still low. Therefore, wire bond, DBC substrate, or anything else outside of these 2 silver plates will not induce the cooling within this 10 millisecond surge transient. Here's the packaging detail of the bottom and double side cooling gallium oxide Schottky barrier diode. First, for the bottom side cooling, here is a gallium oxide vertical Schottky barrier diodes. There's a drift layer, a substrate, nickel and gold forms the Schottky contact, titanium gold forms the ohmic contact. Then we deposit 100 nanometer of titanium and 200 nanometer of silver for the silver sintering. And then we solder it on a DBC substrate, and finally doing the wire bond. And here's the photo. For the double side cooling, it's similar, but we use a flip chip design. And the same story, we deposit titanium and silver for the silver sintering, and we solder it on the DVC, and we do the wire bond. And here's the photo. For more details of the device structure, please read this APL paper. By the way, the Schottky contact area is 3 millimeter times 3 millimeter square, and the total chip area is 4.5 millimeter times 4.5 millimeter square. Okay, so here's the static characteristic of gallium oxide Schottky barrier diodes, and this is the linear scale forward IV. And as we can see that when the temperature increases, the on resistance also increases. The on resistance obeys an equation with temperature over here. And this is the semi-log scale forward IV data. And we can see that the on-off ratio decreased from 9 magnitude over 10 at 33 degrees C to 10 magnitude over 10 at 153 degrees C. But this is also relatively good. Here is the surge test result and analysis. For the bottom side cooling, we can see that the peak current, the peak surge current that the gallium oxide Schottky barrier diodes, which can endure, is about 39 amp. And here's the burning point. We can see that it's an open circuit. There's no current. It's an open circuit after the burning point, which indicates the wire bond burnt. And here's the double side cooling. So the peak temperature that the gallium oxide Schottky barrier diode can endure increases to 68 amp here. Okay, and here's the burning point. So it is not an open circuit after failure. It has a large on resistance after the failure, which indicates a partial burn of the sintered silver contact. Finally is our benchmark and discussion. Contrary to popular belief, gallium oxide Schottky barrier diodes with proper packaging, especially for the double side cooling packaging, shows high surge current capabilities. The double side cooled gallium oxide Schottky barrier diodes with a 3 × 3 millimeter square Schottky contact area can sustain a peak current over 660 amp, with a ratio between the peak surge current and the rated current superior to that of the similarly rated commercial Schottky, the silicon carbide Schottky barrier diodes. Okay, and why is that? The first reason is that if we look at this equation, we can see that the alpha for our gallium oxide Schottky barrier diodes varies from 0.7 to 1.3, but it is around 2.95 for our measured Schottky, silicon carbide Schottky diodes. So the smaller the alpha is, the smaller the on resistance is at higher temperature, and therefore the stronger the surge current capability is. And the second reason is that double side cooling package obviates the heat extraction via the low thermal conductivity gallium oxide chip and moves the peak temperature from the vulnerable Schottky contact into the robust bulk gallium oxide.
Now we're going to measure a double-side cooling packaged gallium oxide Schottky barrier diode with silicon gel protected. Here's the probe station and here's the curve tracer. The diode is in the connection with the probe station now. And now we click measure on the screen of the curve tracer, and then we can see the forward current and voltage signal. In summary, double-side cooling gallium oxide Schottky barrier diode allows the heat dissipation through the gallium oxide chip and directly from the Schottky junction simultaneously, and therefore shows comparable or even superior surge current capabilities as compared to the similarly rated commercial silicon carbide Schottky barrier diodes.